Hello, everyone. My name is João Reis. I'm a producer here at BW Eventstack. I would like to introduce you to Olga Razvenskaia, who will be leading the session Graph Analytics in Snowflake Beyond Traditional SQL. Olga, the floor is yours. Over to you.
Thank you very much. Let's start the presentation. So hi, everyone. I'm Olga Razvenskaia. I'm a senior software engineer at Neo4j in a Graph Data Science team, and I'm really glad to meet you here. So let's start with Graph Analytics in Snowflake. So I think that maybe some of you don't know much about Snowflake, but and for those people, I would like to give some understanding. So first of all, Snowflake is a data cloud, is the cloud-native data platform for storing, analyzing, and processing data. You can do computation, you can create services within this platform, and it supports different types of data which you can store there. And it runs on all major clouds with cross-cloud sharing, and that means that your data stays within your region, and you can have applications right near your data. Snowflake is also heavily investing in AI with features like Cortex AI, which complements the data foundation. I will touch this topic right in the end of my presentation when I will show you how we are doing this Cortex AI integration with in our application. But now let's stick on to the classical graph analytics topic. So why Snowflake matters for graph analytics? First of all, Snowflake holds a lot of data, a lot of tabular data, and users of Snowflake can do SQL queries on this data and get some insights of that. But sometimes you can see that your tabular data actually has graph behind it, and you probably would like to have some graph analytics on your data. And that's why we created our application, which is called Neo4j Graph Analytics, and it's available on the Snowflake Marketplace, and you can install it and have it right near your data. And Snowflake can operate with a really huge amount of data, and our application is also quite capable. That means that we can process big amounts of data with our application. So, and one important thing about that you don't need to extract the data from Snowflake to somewhere else, process it and write it back. Everything will be done within your application, within your account, within your Snowflake account, and it helps to improve performance and make it very easy to access. So every call to our application contains 3 logical steps within the algorithm call. First of all, it will create the graph from your tabular data. It will run the algorithms on this graph, and in the end, it will write the results back to Snowflake tables. So, and all of these steps will be done within one SQL query, and it will be done within one Snowflake account. So a really important disclaimer I would like to share here, that because we are talking here about Snowflake platform and ecosystem, I want to explicitly clarify that our application doesn't use a Neo4j database with this application, because Snowflake itself is a data cloud. It contains a lot of data, and we don't need a special sub part of the application to hold the Neo4j database itself. We can have your data from tables, do the algorithms on that data, and write it back. And one more thing, we don't use Cypher here because, again, it is table-first platform, SQL-first platform. That's why we don't need Cypher here. But we still can think about graphs. We can do graph analytics on the data. And let me show you how your tabular data can be transformed into the graph, into a graph, and how you can do graph analytics on it. So let's dive into some technical details. So the content of all my further slides will be this. So we will start with anatomy of a call. You will see that at the first glance, our call can be quite complex, but you will see the logic behind it, and it will be much easier to access later. After that, we will talk about how we transform tables to graphs internally within our call. I will talk about result types. We will discuss some key feature. I will show you a small demo, and in the end, I will talk a little bit about our workflow and architecture, and we touch the topic of the Cortex agent integration of our application. So my aim today is to build a clear mind map in your brain on how graph can be constructed from the tabular data and how easy it's to do the graph analytics on the data that is stored in tables. So let's go to the topic of anatomy of the graph algorithm call. Here, you see on the very first top line of code, our typical graph algorithm call. For example, here we are calling to page rank algorithm. And as I mentioned before, this whole call will contain three logical subparts. First is the graph projection. Graph projection, we call it projection, and it means that on this step, we defines the tables which will be used to construct the graph within our application. In this part, we have to provide a list of node tables and list of relationship tables. Here, the very simple example with only one node table and relationship table, but I will show you more complex cases later. The second part is the algorithm parameters. For example, here is just one, but actually page rank can be configured in a more specific ways, and we have a lot of parameters to configure your algorithm. And the last one is the part which describes how you would like to see your results in your Snowflake database. So one important part here to mention is you can see this boxed value on the very top line of the code. It is compute pool selector. The only thing you have to provide to choose the proper machine to run the algorithm is this compute pool selector. We support 7 or 8 compute selectors depending on the region. And it can be very tiny machines like XS machine with 1 core and 6 gigabytes of RAM, and it can be pretty big ones with a lot of cores and huge memory. So it is very easy to configure, and we are also provide some APIs to give you a recommendation which pool selector you have to choose, and Snowflake manages the underlying machine provisioning with pay-as-you-go billing. That means that depending on the size of your problem, depending on the machine you've chosen, you will be billed in a proper way. So let's talk about how we construct graphs from tables. It's a very simple example. Let's start from it. For this case, we have 2 tables. The first one the blue one, employees tables, it has a list of available nodes IDs, and relationship tables, which has 2 columns, source node ID and target node ID, which represent connection between the nodes. So it's very intuitive mapping between tables and graph. We support not only the integer ID values, we support also string values as IDs of nodes, and we support the types of connections. For example, even if you have the relationships in your table from source to target, you can add the orientation undirected, and it will double the relationships and connects the nodes in a backward direction. We can also introduce different types of nodes. For example, we can add to our persons who likes some instruments, and the relationship type will connect persons and instruments. And it is also available, the one more feature which is available here, that we can provide different types of relationships. And for example, here, airports in countries relationship table connects airports and countries, and roads table connects airports with airports. So each relationship table defines a distinct relationship type. So the very important things to mention here is that we have quite a strict requirements on the schema of the table, because we have to rely on some specific information when we construct the graph in our application. So our node table must have a node ID column, and its name will be translated to the node label. We support integer and string values as node ID types, but for properties, we support only numeric values for nodes, same as we have for graph data science package. For relationship tables, there are some different rules, like they must contain source node ID and target node ID. This is how we understand which columns should be chosen to get the source and target nodes. And the name of the relationship tables defines the relationship type. So if your data, if your data doesn't satisfy these requirements, we suggest to create views to avoid data duplication, but make it possible to run the algorithms on this particular data. So this is the table represent the difference between property graph model, which is used in Neo4j, and graph represented at tables models, which is used in Neo4j Graph Analytics on Snowflake application. So nodes from Neo4j becomes rows in nodes tables. Edges becomes rows in relationship tables. And properties and attributes become values in some particular columns. We have some restrictions on the number of labels. For example, in Neo4j, in a property graph model, you have none, one, or multiple labels for every node. But for graph represented at table model, you have the only one label to a node. So we use Cypher query, like query language, graph-specific query language like Cypher for Neo4j, and we use SQL for our application. And there are some other things that we can compare that you can see it and read it from slide. I just wanted to highlight the differences between the graph in Neo4j database and graphs in the Snowflake, which we can construct from tables. So at this moment of time, all the algorithms highlighted in blue are available in our application. So right now you can go to Snowflake, install our application, have a 30 days free trial and test it on your data. So we added almost with every release, which we do quite often. So expect even more algorithms available soon. So now let's talk about the result types that can be produced. We have 3 types of results that we can produce. This is the results for nodes, for relationships, and a special type of relationships result, which is a path result. Let's have a look. So node results is a results which are computed for every node on requested result table. It can be integer value, vector or embedding value. It can be floating point value. Relationship results computed for every relationships on requested result table. So, for example, we can compute some similarity scores, for example, as you can see on this screenshot, for some pairs of nodes. And we are also provide the path results. This is the type of result which represents the description or the parameters of the path which can be obtained with one of our algorithms. So, and you can see here that these clusters of algorithms produce some specific types of results. So yeah, everything is on slide, so we can move forward. So, as I mentioned before, we can provide you a clue or recommendation on which compute pool selector should be chosen for your data size or for your algorithm you would like to run. And the only thing you have to do to get this estimation is to change this schema name from .graph to .estimate experimental. It is our experimental API, but soon we will promote it to our common list of functions. So yeah, and the result of this call will be a JSON structure, which will have a pool selector, an estimated number of amount of memory that will be used for the algorithm, and also some statistics on some size information on the data that will be projected. We're also having visualization capabilities in our application. At this moment of time, we have it as a separate package, which is available on Snowflake with the Conda channel. And it is open source one. And actually, we have a dedicated session from Adam and Florentin, which will talk about it in app development conference part. So if you want to see more about this particular package, please join the presentation, which will be, I think, in a little bit less than 3 hours. So this time for a demo. So I prepared for you the notebook with the data about flights, and we will run the PageRank algorithm. Right now, I click Run All button, and while I'm going through this code, we will have the results of the application. So I've got my data from OpenFlight's datasets, and as you see here, as I suggested on several slides before, I create a couple of views, which the main aim for creation these views is to require this column, but some particular column names for our application, like node ID for node table, and source node ID and target node ID for our relationship table. So it's a quite typical code for everything in Snowflake. You have to grant some permissions to your application to use some specific data for your database and grant some permissions to write results back. So it is nothing special. This is just how Snowflake works. So here I switch to the role which will run the algorithm. So here we see that the algorithm PageRank right now is running. What is happening behind the scenes? So it got the graph from these tables. It starts the machine. I use XS size machine here, and I run the PageRank algorithm with some additional parameters here and write result in the table. We see that job status is success. The job was successful. We have some statistics on that, like for example here, and we also can obtain the. Here we provided the name for the result table, and we can obtain the result for this table. We can obtain results stored in this table. And here I create a view which will help me to join this information with the full information about the cities, countries, and names of the airports. And I can create, select several nodes and several relationships between these top airports nodes to have them visualized. This is the Neo4j Viz package. And we call from Snowflake function in that and provide exactly the same configuration which can be used actually for computational part. And here we've got the visualization. Woohoo! That was a successful demo. I'm so happy. So let's go back to the presentation. The job lifecycle. So a user calls the application specifying the desired instance size. We validate the provided arguments and do checks if everything is right. Do the columns have the proper names and so on and so forth, and give you a nice error message if something went wrong. So after that, we run the job in a Snowflake Container Services, and Snowflake launch the Docker container on a machine with CPU or GPU, which you specified with compute pool selector. It runs GDS algorithm or special or other algorithm. For example, GraphSage. We have currently GraphSage implementation, which is written in Python. So for some algorithm, it will run Java algorithm. For some, it will run Python algorithm. And in the end, we store our results in a table and provide them to you back. So, and the future, conversational graph analytics. As I mentioned before, we are experimenting on Snowflake agent with integration with Snowflake Agent, and now we have a prototype. Probably we will release soon this thing, which allows you to construct this maybe sometimes quite complex configurational JSONs for the SQL call, and it will help you to figure out which way is the better for construct them. It can help you to provide the overview of the available parameters right in the chat window. And it also can help you to analyze the results, like, for example, to get some best values based on some metric, or check if they are, for example, if the nodes with higher, the largest PageRank score belong to the same component, for example. All these things will be available soon, and they are possible. So we have a lot of things in future and hope it will make it easier to use. So we've got quick start guides. We've got GitHub examples. Links are here. So two important links. The first one is the documentation. It has all the information about parameters, available algorithms, the best practices, guides, how to establish the connection, how to grant all the proper things you have to grant to application or a role. And this is the link for our application. So please try it, enjoy it, and thank you very much too.